What up, guys? Today we are looking at another problem in Griffiths. It's an interesting problem because we're going to use an argumentative method to solve it. So we're going to argue our way to a solution, which means no crazy math. I'm just kidding, guys. There's going to be a ton of crazy math. It's going to be fun. We're going to learn cool things about differential equations. We're going to learn cool things about the Schrödinger equation in specific. The problem here is important. You can see it has a little star on it right over here. And these problems with the star are very important to do. Griffith says you got to do these problems. So we're going to read it out. And I'm going to take a little bit of a segue and explain to you guys some interesting things. We're going to work with the Schrödinger equation a bit, and then we're going to solve this problem using this argument method that they're trying to point us to. So let's read out this problem. It says, problem 2.2, show that E must exceed the minimum value of V of x for every normalizable solution to the time-independent Schrödinger equation. Nice. What is the classical analog to this statement? Hint, rewrite equation 2.5. I'm assuming 2.5 is the Schrödinger equation. If it's not, I'm going to throw it up on the screen right now. But rewrite that equation in the form, boom, and they give us this form here. So this is what we're going to start working with. Then they continue the little hint. If E is less than V min, then psi and its second derivative always have the same sign. Argue that such a function cannot be normalized. Okay, so where do we start, guys? First, I think it's important to just write out this equation. So we have the second derivative of psi with respect to x. This equals 2m over h bar. And then in these brackets, which is the important modification they've made, they do v of x, which is the potential, minus the total energy, E. And then they put the psi there. So V of x is related to your system. This could be the particle in a box. V of x is 0 when you're inside the box. Inside the box, the particle is free to jump around. There is no potential. Potential is literally like, imagine you're attached to a pulley, or imagine you're attached to a pendulum, or imagine you're attached to a spring, or you're running around the earth. All of these scenarios have a potential. The potential on Earth is the potential of the gravitational field. On a pendulum, on a pulley, you are attached to a rope. On a spring, you're attached to the spring, so you feel the force of a spring. All right, so in the box, you have no potential. Nothing is affecting you. You're just free to roam around. But as soon as you hit the walls of the box, there's an infinite potential pushing you back in. So this is why the particle is stuck in the box. The free particle is defined where V, the potential, is 0 everywhere. So the particle can just boom, fly around wherever it wants. The harmonic oscillator has a parabolic potential, so it is stuck within a parabola. But in quantum mechanics, you can see that there's actually some tunneling, so the particle can escape out of the walls a little bit. There's a non-zero probability. And there's some other potentials like the Dirac delta function potential, the hydrogen atom potential, all of these things. So this is something related to your system. You plug that shit in, you solve the Schrödinger equation, and you get interesting things like steady state wave functions, energy, stuff like this. So that is what V is. And the total energy is the total energy of your particle, which is the potential energy of the particle plus the kinetic energy of the particle. This is the total energy. Or in some quantized systems, the allowed energy states. You saw this with the particle in a box. You can only have a specific determined amount of energy. So that's just a little bit of background for you guys. Now let's take a look at this equation. All right, they're talking about this case over here. This E is less than V min. So I'm going to write this down, E less than V min. And you know what? I don't really like V min, so I'm just going to change it to E is less than V of x. All right? If E is less than V of x, then what happens? Then let's do V of x minus E. What is this going to equal? Well, E is less than V. So if V is bigger than E and you subtract E from it, then this will be a positive number. Positive num. All right, then there's another scenario, which they don't write in the book, but it's a natural scenario to think about. V min. I also don't like V min because it's not in our equation. In our equation, what we have is V of x. So let's just switch this out for V of x. E is greater than V of x. Then what happens? Well, if we do V of x minus e. This equals, let's think about it. E is a big number. And if you do a small number, v of x, minus a big number, e, then here you must get a negative number. Right? So literally what I'm doing is checking out what happens here if e is less than v. So if e is less than v, then this thing over here spits out a positive number, right? And here you have positive numbers, here you have positive numbers. So everything in front of this psi over here is a positive number in this region. In this region, right, where e is less or e is bigger than v, then you get a negative number. So this thing inside here is a negative number. If you multiply a negative number by these positive numbers, then everything over here in front of this little psi is going to be a negative number. All right, does that make sense? Now let's do some simplifications. Let's take this equation over here, all right? We're going to pull this, boom, throw it down here and rewrite it. So what we had was the second derivative of psi with respect to x. This equals some stuff, and now I'm going to call this stuff k squared. And I'm going to put a minus sign in front of it. All right, what is this k squared stuff? K squared is equal to everything inside here. So this is 2m h bar, and then here we have this v of x minus e. So I just replace all of that stuff here, everything here, by this different symbol, k squared. And I'm using k squared suggestively because in the future you're going to see something happen, and calling it k squared is a bit more natural. If you want to call it a, b, c, if you want to call it like, I don't know, weird letter like alpha, you can do that. If you want to call it just k with no square and no negative sign, that's okay. But let's use this over here and see what happens, because all we do here is simplify this differential equation. This is a differential equation. Here is the derivative, is a second order derivative with respect to x, and psi here depends on x. Over here, this is the time independent Schrödinger equation, right? They say that over here. So psi only depends on x, which is why we have a full derivative over here. So on the left-hand side, we have a derivative of psi. And on the right-hand side, we have a bunch of constants. All of these things are constants. We're going to treat them as such. And then here we have the function itself. So once we simplify it in this form, we just have to solve this differential equation. If you're a mathematician and you know how to solve differential equations, this is where you start grinding. But I have a strategy of remembering this, and it is a pretty simple strategy. I'm going to write it down here in red. Basically, I'm going to ask what function f equals its second derivative. And I'm using primes here to denote derivative. This is the same thing as saying what function x equals its second derivative, written like this. The only functions that I know that do this thing are sines and cosines. Sine of x, cosine of x. And you know what? Instead of just having x in there, I'm going to put another letter in there. Let's call it k, right? Because that'll be more interesting. Instead of just 1x, we can have kx, and k could be 1, 2, 3, pi, 15. It could be e, whatever. It could be anything in there. So let's take a look at the derivative of sine of kx. How I remember this is the derivative of sine is cosine. So this is going to be a cosine kx. And since you have a function within a function, right, kx is its own thing inside sine. We have to use the chain rule, and we basically take the derivative of what's inside this over here. So the derivative of kx with respect to x is literally just k. So this thing spits out a k over here. Nice. Now let's get some more room and check out the derivative with respect to x of cosine kx. See what that equals. I remember cosine is negative sign, so it just repeats back, but with cosine you have a negative sign in front of it. So we have a negative sign, we spit out that k again, and then we have a sign over here, kx. Nice. If you guys don't remember this, check out some derivatives of trig functions. No stress if you forgot it. All right, but then from here, from this derivative, we can go back over here, right? So if I take a derivative of negative k sine kx, I get back to cosine again. So basically what we're saying here, and this is going to be the important thing which I'll write in blue, the second derivative with respect to x of sine kx is equal to negative k squared sine kx, right? So we take the derivative of sine once and we go to cosine and we have a k here. We take the derivative of cosine kx. This k jumps out of the derivative because it's a constant. Another k comes out of here, right, because of this. So k and k give you k squared. And then the derivative of cosine spits out a minus. So here's the minus. And the derivative of cosine is sine. So here we have the sine. And the same thing happens with cosine. So I guess I'm going to just write this over here. The derivative, second order, of cosine kx is equal to minus k squared cosine kx. All right, let's see how this works. So here we have derivative of cosine gives you minus sine. So we already have the minus one. We have 1k. And then we take a derivative of sine. This k comes out of the derivative, right? It's left here. The derivative of sine gives you k cosine kx. So this k combines with this to give you k squared. We have a minus sign from the first derivative, and we have cosine over here. So both of these things, sines and cosines, are solutions to this differential equation. This is why this minus is left over here, and this is why this k squared is left over here. I hope you guys feel okay with this, but what you might be asking is, why did I put this random minus sign here, and why did I call this k squared? K squared is to make this just seem a little bit more clean in the end. Originally, I could have just left this as k, but then if I want to find out what k is, I have to take a square root of all of this thing. So to keep it a bit simple and not square root anything, I just call that whole thing k squared. And then knowing that this gives you a solution in terms of sines and cosines, and the second derivative spits out the factor in here twice, I just call this thing k squared, and then we're good to go. Basically, renaming this constant here. You can rename it anything, like I said, but we're going to rename it k squared. Now let's talk about this minus sign, because this minus sign is going to give us the solution to this problem here. All right, they're asking you, if v is bigger than e, if e is less than v, then psi and its second derivative always have the same sign. Argue that such a function cannot be normalizable. Okay, so what we were talking about here. If e is less than v min, here we wrote down the case. If e is less than v min, e is less than v of x, then what happens is v minus e, this thing in here, gives you a positive number, right? If this number is positive and this number is positive, then the thing in front of psi is going to be a positive number. It's not going to have this negative sign here. So I added this negative sign kind of prematurely. It's kind of like how I knew this k squared was going to pop out. So this minus sign is specifically looking at this case here, where e is greater than v min. What is happening here? E is greater than v of x, and then v of x minus e, which is this thing right here, is going to give us a negative number. So this negative number, whatever, it's some negative number, whatever it is, right? This negative gets pulled out here. We call everything else over here k squared, and this gives us minus k squared, which is exactly this scenario here, which gave us solutions to that scenario, which are sines and cosines. All right? I'm building up to something here. So if we saw that these are solutions, then let's check the scenario where we have a positive number over here. So we're going to literally take this exact equation. I'm straight up going to grab it like this, duplicate this guy. Actually, no, I can't duplicate it. I'm going to have to copy it, go to another page over here. And let's call this plus. Right? This doesn't work now because, as you guys saw before, this minus sign is necessary if you want sine and cosine to be solutions to this thing. So now you have to solve a new differential equation. A differential equation where the function here and its second derivative equal each other with a positive constant. So I just gave you guys this thing over here. If you're a mathematician, you can find your own way of solving a differential equation like this. How I remember it is I ask myself, what function do I know that equals its second derivative? We have sines and cosines, but it only equals itself with this extra minus sign here. So now I have to ask myself, what function do I know that equals its second derivative, but the factor it spits out is a positive number? So I'm going to start thinking again, and I think I have a function in mind. The function is an exponential. Let's call it e to the kx, right? E to the kx, if you take the derivative, so f prime, or I guess let's use our previous notation, d dx of e to the kx. So the derivative of an exponential like this is the exponential itself. It doesn't change, but because of the product or the chain rule, right here, we spit out a k in the front, and it's just a positive k. Now if we want to take the second derivative, we can do this as well, e to the kx. It's literally going to be the same thing, except since we differentiate twice, we spit out k squared, and this gives us the solution over here. All right, so that's pretty cool. Now we have solutions, two different kinds of solutions. This one is an exponential, right, over here. So an exponential function looks like this. It just goes yeet all the way up. Here we are plotting e to the kx. Here we are plotting k. Sines and cosines, you guys know what they look like. I think sine starts here. It goes like womp. It starts at 0, right? Boom. And then cosine starts at 1 and it goes down. Maybe these are not too much to scale. Starts at 1, yeah. Boom. So sines and cosines oscillate like this, but exponential functions increase. So you can see here we have two differential equations. One of them has a minus sign in front of it. The other one has a plus sign in front of it. Other than that, the form is almost identical, but they yield different solutions. The one with the minus sign yields oscillating functions, sines and cosines. But this one here with a plus, it yields an expanding function like this, an exponentially increasing function. So what can we get from this? Well, let's go back to the problem. Let's check out what they were asking us. It says, show that E must exceed the minimum value of V for every normalizable solution to the time-independent Schrödinger equation. I'm going to underline this, for every normalizable solution to the time-independent Schrödinger equation. What is the classical analog to the statement? We're going to get to that in a minute, or maybe near the end of the video. Then at the bottom it says, if E is less than V min, then psi and its second derivative always have the same sign. Argue that such a function cannot be normalized. So we just saw here that this scenario yields a positive number right over here, right? If we rename all of this stuff k, or k squared, whatever you want to rename it, k squared. If you rename it k, then k will be a different thing. Like it will be a square root of this thing. But if you rename it k squared, then k itself will be this. I hope that made sense. But in one scenario, if the energy is less than the potential, then you'll have a positive number here, and the wave function will be this thing over here. This is not normalizable. What does normalization mean? Normalization, which I'm already in pink over here, says that if you take the integral from negative infinity to positive infinity of psi, specifically the absolute value squared of the wave function, or you can take psi star psi, if you want to be complex about it, then this thing should equal some finite value. It shouldn't blow up. And actually, in quantum mechanics, we force this thing to be 1 because we treat psi as the probability distribution of the particle in question. So take a look at this. This thing blows up to infinity. The area under this thing, or specifically, if you plot this thing absolute value squared, this thing always increases. So this area blows up, and there's no way you can normalize this to 1 because this area is always huge. It gets bigger and bigger. There's no way to normalize it. If you look at this area here, it also looks kind of weird. I mean, you have some area here, you have some area here, here, and so on. So how are you going to find the area under this thing squared? Well, think about what the absolute value squared of a sine or cosine looks like. So here I'm going to plot x, and I'm gonna just plot sine of kx. So sine of kx starts at 0, and it goes like this, and it goes to the negative sides too, whatever. But now we can also plot the absolute value squared of sine. Sine of kx squared. What does this look like? If you plot the absolute value squared of sine, it basically flips all of the negative things up here. I think it looks something like this. Boom, and it just does this. Okay. So if you get the area under this stuff and you add it up, it also looks like it blows up to infinity. So what's happening here? I guess an argument could be, in the particle in a box, you kind of cut off the area here. Right? This is the particle in a box, and inside the box, it's doing some oscillatory behavior. And this you can normalize. But why can't you do that with this? Can't you just cut this off here and then this area you can normalize? I'm actually unsure. So basically what I'm trying to show you guys is that depending on the relationship between the energy and the potential, right? If the energy is less than the potential, then over here in front of the psi, you get a positive number. And this function, or this differential equation, gives you solutions of exponentials. And exponentials are not normalizable in quantum mechanics. So we throw them out. Mathematically, this is a solution. But quantum mechanically, we don't want to look at it because it doesn't represent a physical particle, because it is not normalizable. But if the energy is greater than V, the potential, then you get a negative number here, and you get this differential equation, which gives you oscillating sine and cosines, which are normalizable, I think. I'm missing a little bit of knowledge here. I don't really know why a exponential is not normalizable, but a sine and cosine is normalizable. But I'm just showing you guys this here. Maybe you guys have an idea. So what I wanted to talk about as well is, if you have the Schrödinger equation, here we have, do we have h bar, or do we have, let me check, 2m over h bar. 2m over h bar, and there, here we have v of x minus e psi. In the free particle and the particle in a box, there are regions where v of x is equal to 0. So if you plug 0 in here, then this thing gets removed. There's a minus e. So everything over here, you can rename k squared, and because of this minus sign, you get a minus sign in front of here. So the particle in a box gives you solutions in the form of sine waves. And the free particle does this as well. However, for the free particle, there's one important thing you guys gotta know. E to the ix is equal to cosine. E to the ikx, maybe we should do. Ikx is equal to kx plus I sine kx. So imaginary exponentials with this I over here can be rewritten as summation of sines and cosines. So for the free particle, it's nice to write it like this because it represents traveling waves a little bit better. But for the square well, you don't need to do this because the boundary conditions kind of remove one of these, and you don't have imaginary solutions either. So you could just use a sign to talk about the particle in a box. So let's go back to this solution and see what we can argue here. If E is less than V min, then psi and its second derivative always have the same sign, argue that such a function cannot be normalized. Okay, maybe what I can say is this. What we have here is this growing function, and it is represented by this differential equation. There's the same sign here as there is here. One final thing I wanted to say, and I'm actually just copy this. Maybe this will solidify our argument. So Do you guys remember in calculus when you learned about the first derivative and the second derivative and what they mean? So the first derivative, f prime, tells you about the slope or rate of change of a function. So if you had just a linear function, this blue function is going up, so this has a positive first derivative. And this red function over here is going down, so it has a negative first derivative. You guys remember this? What you may also remember is that the second derivative of a function tells you something about the concavity of a function. So let's say we had a parabola, perhaps. This parabola, since it's concave up, it like opens up, its U shape is going upwards. This has a positive second derivative. But if you had another parabola going down like this, then this has a negative second derivative. So okay, there's an argument you can make here, and I saw this also in the solutions of the Griffiths book, specifically to this problem. It's saying that if this function, psi, has a positive value here, and its second derivative over here has a positive value, it means it is concave up, and its value is also increasing. So if both of these things are happening, it means it is running away further and further from x, or from, it is going further and further away, basically blowing up. This is how I hear people talking about, I'm not that great at mathematics, but they say that the function blows up as x goes to infinity. So as x goes to infinity, this thing goes up, boom, there's nothing you can do to normalize it. With this one over here, you have a negative second derivative. So sometimes, well, it seems to be concave down this way and concave up this way. So it changes. And this is again where I'm lost, guys. Like, I don't really know how to argue this. But I think this argument here, let's say you're doing a quiz and you're talking about this, I would break it down like this. I would say, okay, what's happening when E is less than V min? I'm going to talk about this, plug this in, and then use this differential equation to simplify like this. And then show that this equals oscillating sines and cosines. Then I'm going to say, okay, oscillating sines and cosines, these are differentiable, or these are, what is it called? Normalizable, so it's chill. But then something like this, when E is less than V min, this blows up as it goes to infinity, and this is a non-normalizable function. So maybe this is some homework for me. Figure out why sines and cosines are normalizable and why exponentials are not normalizable. I'm going to try to do this. I'm going to try to give you guys an answer in the next video or in the comments or something like this. But one other thing we should say is, what is the classical analog to this statement? Okay, so what we basically said is if E is less than V min, so the total energy of the particle is less than the potential energy of the particle, it's not possible. The particle cannot exist because the wave function is not normalizable. So E less than V min, this cannot be. But if E is greater than V min, then this is good. So what is it saying about classical analog? Let's think about this. So I'm going to zoom in right here and just use this little space here to work. Let's work in this orange color. In classical mechanics, I remember 1/2 mv squared is equal to the kinetic energy, right? And then V of x is the potential energy. And then the total energy is equal to the potential energy plus the kinetic energy. If E is less than the potential energy, what does this mean? E is less than the potential energy. That means the kinetic energy must be negative, right? From this equation here. if E is less than potential energy, so we have this number here, and this number is bigger than this number. Yeah, the only way that can happen is if this thing is a negative number. Because if this thing was 0, let's say this thing was 0, then these two would be equal. That's not what's happening. E is less than this, right? So the only way that can be is if there's negative kinetic energy. What does negative kinetic energy mean? It doesn't make sense, right? Because kinetic energy is defined as 1/2. This is always positive. Mass is always positive. And velocity squared is a squared number. It's always positive. So what's going on here? What is the classical analog to this statement? Show that E must exceed the minimum value of V of x for every normalizable solution to the time-independent Schrödinger equation. Okay, let's zoom in here a little bit more and write in this color. So if E must exceed, so E is bigger than V min, then what happens? Potential energy plus kinetic energy is equal to energy. Energy is bigger than V min, right? What does this tell us? Let me think here. I guess kinetic energy is positive, huh? Kinetic energy is big. E is big. Yeah, bro. Positive kinetic energy. So you're chilling. Argue that such a function cannot be normalized. Classical analog to this statement. The classical analog to this statement is you cannot have negative kinetic energy. And we just showed that E must exceed the minimum value of V, meaning E must be bigger than V min, because if it wasn't, then you would have a non-normalizable solution. Thank you guys for watching. I will see you guys in the next video. Let me know if anything here did not make sense. Let me know if you want to see other videos like this. This is a very important problem. He marked it with a star. So if you guys don't know what I just said here, try to solve this problem on your own. Try to check the solutions. And yeah, talk to your family and friends about this and see what they think. See you guys in the next video. Thank you guys as always for watching. Peace.